Today we're going to demonstrate and talk about electricity. The concept of electricity has actually been around for thousands of years. Lightning bolts have been hitting people, and people have been doing electrical reactions without knowing it. It wasn't until the mid-1800s that we finally harnessed electricity, and this is an example of electricity running from the center sphere over to the outer sphere, and we can see the plasma as it goes. So we're actually watching the flow of electricity as it's being conducted through this plasma ball. Now, in chemistry, we like to label all the compounds as either strong, weak, or non-electrolytes. So I'm going to put the plasma ball down for this moment. And we have an old tester that used to be our lab equipment. It basically has two N filaments that when something conducts electricity, the light bulb turns on like so. And if you use something that doesn't conduct electricity, it will not turn on. And the amount of electricity that goes through, shown in the relative brightness of the light. And one of the things we've discovered is that is directly proportional to how many electrolyte ions are floating. So the first myth we always have to remove is, does water conduct electricity? We have here some ultra pure water. When my kids were watching the Pokemon show, whenever Pikachu was in trouble, they just doused the Onyx in water and it'd be electrocuted. Now I just put my electrodes into the water, and can you see the light bulb turning on? And the answer is no, this one is a non-electrolyte. So if water ever shows up on your quiz, please put non-electrolyte. Okay, so we have water. What we're going to do is add chemicals to the water. And the two most common chemicals tested are household chemicals, sugar and salt. So I'm going to scoop some sugar into one. And I'll scoop some salt in the other. Hopefully I'll scoop some salt in. Okay, make it approximately the same amount of compounds in each of these. We're now going to add the pure water into both, about the same amount, and do a fast stir. And both of these compounds are very good at dissolving in water. So we're now going to test them with our conductor and see which one conducts electricity, or both of them do. So we're going to take the light bulb away. This is the salt. The salt hasn't finished dissolving, but if we put it on here, ooh, we get a nice light bulb glowing. And for this class, sodium chloride is a strong electrolyte. Okay. We're going to rinse off the electrodes briefly. And we're going to now try it with the sugar. And we add the sugar and we let it sit and we let it sit, and there is no electricity. So sugar is a molecular substance. It does not break up into ions when it dissolves. It stays as intact molecules. And so we classify all sugars as non-electrolytes. Okay. Other compounds, ionic compounds, we're going to do two tests now. Calcium sulfate and magnesium sulfate. So this one is calcium sulfate. These are the classic milk salts that come in your milk. And if you drink skim milk, this is all you're drinking, are the magnesium and calcium sulfates. Okay, to both of them, we'll add pure water again. We just made some skim milk. Very nice. Okay, now let's dim the lights down again, and we're going to test them. So the one on the left here, or your right, is the magnesium sulfate, and you see the light bulb shines nice and brightly. I'm going to rinse off the electrode now. And we'll place the calcium sulfate in it, and you'll see that it barely glows. Calcium sulfate, can we even see the glow? Oh yeah. Calcium sulfate is actually classified by some chemists as a moderate electrolyte. Well, that's not allowed in our class. So we're going to classify calcium sulfate as a weak electrolyte because he does not glow the same as a strong electrolyte like the magnesium sulfate did. So both calcium sulfate give a little bit of conductivity. Strong electrolytes like this compound we assume dissociate nearly 100%. Weak electrolytes only partially dissociate and they stay together. Now, acids are classified in the same principle. Strong acids dissociate completely, weak acids do not. So I'm going to use two acids of everyday life. The one here on your right is stomach acid. The one here on your left is acetic acid, also known as vinegar. Now, what we've done is we've done the exact same concentration of compound dissolved in water. These are both at 0.1 molar solutions. So, same amount of compounds dissolved into the pure water. Let's see what happens. So, first the stomach acid, also known as hydrochloric acid. Wow, as soon as I touch it, you see how intensely bright that light is? So hydrochloric acid, we're going to use in today's lab as an example of a strong electrolyte. And here is vinegar. Come on, vinegar. It'll glow eventually. Oh, if you get up close, let me turn off the light. There's a tiny glow of the filament. Let me see if you can see it if I put a black behind it. Can you see the tiny glow of the filament?
No.
No? Should I zoom in?
Can I bring it closer?
We are. Okay. You might need to turn off the other light that's in this room. Okay, the vinegar. Go ahead and turn off the other light. We're going to hold this up as close as I can. And we lost all camera.
Nothing?
Oh, I can see it glow with my eyes, but the camera disappears and goes completely black.
Well, they're gonna have to believe us.
Yeah,
Very
apparently
faint.
it's a very faint glow. It's like you can make out the filament and that's about it. So what does that tell you about acetic acid? Well, acetic acid dissolves completely in water, but does not hardly dissociate at all. And so an acid is classified as weak or strong. In today's lab, you are going to use hydrochloric acid as your standard for a strong, where's my hydrochloric acid? That one. As an example of a strong acid. And so what we're going to do, instead of using a light bulb, we're going to measure the conductivity with an electrical probe to actually measure how fast electrons conduct. One of the cool things about acids, the hydrogen ion is the fastest conducting ion there is, and so you always have higher numbers with acids than you do normal ionic compounds. So we're going to reference conducting and dissociating completely with hydrochloric acid. Conversely, with ionic compounds, one of these is salt, one of them sugar. Let's see which is which, I forgot. Oh, that's the salt. So whatever the conduction is for salt, sodium chloride, we're going to give that the conduction for 2 ions. Now the number of ions is very important. If you have more ions, the conduction goes higher. If I have less ions, the conduction goes lower. And I'm going to demonstrate that simply by pouring out half of this water, filling it up with more water. So even though it's exactly the same compound as it was before, it's still shining brightly. We're going to dump it in half again. We're going to do an edit on that. Okay, so I reduced the number of ions and you see the conduction of the light bulb has dimmed. In the lab today, we are going to do a proportionality of the number of ions versus the amount of conduction that the computer records. It is whether it conducts 1-to-1 or it does not, like in the weak cases. Your job is to see if there is a direct proportionality to the number of ions with the same concentration versus the conductivity. Now, the last thing that we like to demonstrate today is elastic pickles. Can you see the label? We have elastic dill pickles. Dill pickles are prepared. I have here strapped to a piece of cardboard pickle that I took out of the jar. I have 2 wires that are stuck into it. You want to shine the light for a moment right on the pickle. See the 2 copper wires are sticking into each end. They're not a thing. And the 2 copper wires, the other end of them go to this everyday looking plug. So basically all I'm going to do now is plug the pickle straight into the outlet. And we're going to watch what happens. And this is typical of a elastic dill pickle. So the question is, what does that mean is inside the pickle? I'll give you a hint. Do they make pickles? They either use sugar or they use some other compound. I want to try multiple pickles now. No, don't record right now. Okay, guys, don't do this at home. Okay, what I'm doing right now is I'm taking 6 pickles and I'm connecting them together through 10-gauge wire that I had left over from a side project. I'm just going to see if it works, and if it works, it doesn't blow up.
No explosions yet.
Yeah, it only explodes if you build up pressure inside the pickle and it pops. Question is, do we have enough, or do we have too much resistance and can't conduct electricity?
It's smoking over here. Oh, it's alive!
We got one alive. We are completing the circuit, but the other guys aren't going. This one almost is. They're smoking. Now this one's going.
You get this down really good, it can be like Christmas ornaments.
Okay.
Have it go with music.
All right. Now we're going to do it in parallel.
And it's still rolling.
Still rolling?
Yeah. Oh. I saw sparks somewhere. Oh.
I got all 6 of them to go for a moment. And the third one's kind of resisting. Look at that. I made them in parallel this time. All right, is that enough glowing? Ooh, that bottom one really is glowing good. Well, we don't want to blow out and shut out the circuit. Okay.
Well, this week's laboratory exercise is an exercise in measuring the conductivity power of electrolytes and non-electrolytes. This week's lab is brought to you by Brondo. If you don't know what that is, consider yourself lucky. So what is an electrolyte? An electrolyte is a substance that dissociates, and so it's a substance that where the elements break apart and it fully ionizes, or partially. Okay? So why do we care about this? Electrolytes are an important part of many scientific and biochemical processes. They are the means by which electrical signals are conveyed through a water-based medium. So it's how a lot of messages are transported across the membrane in the living system. It's the reason why if you put salt into water, it will actually light up a light bulb. It's actually the basis for most batteries, that they contain an electrolyte substance that dissociates, and as they dissociate into water, they release temporarily their electrons, and the movement of the electrons conveys an electric current, and this current can be measured. Okay? So what we're going to do is we're going to use what's called a conductivity meter, conductivity probe or meter. Okay, and it's just a cylindrical probe that's connected to a computer that you will then put into a beaker that contains the solution of choice. And there's a sensor inside of the conductivity meter that will detect the electrical current and the movement of electrons in the solution. So we're going to use this conductivity probe, first of all, to differentiate between is it an electrolyte or is it a non-electrolyte? And if so, what are the strong electrolytes? Because this has relevance to other topics of chemistry like colligative properties and the net ion effect. And we'll deal with colligative properties in another lab at the very end of this semester, but the net ion effect tells us that what happens essentially is that if you have an ionic substance that is an electrolyte, then once it goes into water, it has a magnification of the concentration of solutes. Okay, so for example, if you have 1 mole of sodium chloride, once you put it into water, it becomes sodium ions and chlorine ions. And so once it's dissolved in water, it has 2 moles of net ions. So similarly, for example, iron chloride gives us 1 mole of iron ions and 3 moles of chlorine ions. Okay, so 1 mole of solute gives us a net ion effect of 4 moles of ions in the solution. So, okay, so a strong electrolyte is something that dissociates completely. And I can tell you right now that this sodium chloride is a strong electrolyte, and this is a weak electrolyte. Okay, so strong electrolytes, because they dissociate more, will have a greater electronic charge created than those that are weak electrolytes. And we can measure this and then rank them in terms of their relative strength. Okay, so in the experiment today, we're going to look at 3 different groups of substances. We're going to look at ionic compounds. Okay, these are substances that typically dissociate 100%. That makes them strong electrolytes. And you can tell whether or not something fits into the ionic compound category because you can look at the strength of the bond between them and the differences in electronegativity. And if the difference in the electronegativity is greater than 1.9, then it is going to be, you know for sure that it's an ionic compound and will dissociate completely. So we have a series of substances that we're going to look at today which definitely are ionic. Secondly, we're going to look at molecular acids. Okay, these are typically weak electrolytes, but they are electrolytes because all acids are compatible with water. So they will interact with and dissociate in water, and the anion portion of the acid is typically an ionic substance, and so there is a minor or weaker electrolytic effect. Okay, so we'll be able to measure that and look at those and look at whether or not they are strong electrolytes or weak electrolytes, but many of them are weak electrolytes. This also plays into whether or not they are strong acids, because strong acids means 100% dissociate. Okay, and 100% dissociation means strong electrolyte. So strong acid also equals strong electrolyte. And that's one of the things that makes a substance a strong acid. And so we're going to look at and rank them based on their conductivity. And finally, we're going to look at molecular compounds. And that is all other solutes that are compatible with that will dissolve in water. So we're going to look at a few other materials that will interact with water and measure whether or not they are what contribution they make to the conductivity. So the many things dissolve in water. Bleach dissolves in water. Ammonia dissolves in water. Glucose dissolves in water. And so those are other things we could look at. And because some of them may or may not have any ionic portions, they may or may not actually cause an increase in the electric charge. So we're going to look at these in 3 groups and look at these substances, collect their conductivities, and then rank them based on their actual electrolytic state. Okay, so for the next part of the lecture, we're going to go into the lab then and look at the actual conductivity probe, how that works, and set that up for you. All right, so the probe we're going to be using is connected to this vernier interface. And as you can see, the probe is sort of how we drew it in class. So there's a passageway in here that it gives access to the probe inside, and it will measure the electrical conductivity there, and then report it to, and then the software will report it into this format. So we've already loaded a macro into the Logger Pro software suite that sets this up to report what we want in our report. So across the bottom here, you see there's the trial number. So each substance we measure will appear under, trial 1, then trial 2. And then on the x-axis, on the y-axis here, we have the conductivity in microsieverts per centimeter, and that's how conductivity is measured. So it's going to give us a graphical representation here, but also in this section up here on the left-hand side, it will put it into a graph. So if you watch right down here in the bottom left-hand side of your screen, that's the number you're going to want to record when we take our readings. Okay? In between each of our substances, we're also going to rinse with DI water. That's to make sure that we have removed any residual electrolytic compounds from the probe. So without further ado, we're going to start with aluminum chloride. Okay? So I've already taken the liberty of putting some aluminum chloride into this beaker, and we are going to put our vernier interface into the beaker containing our substance and measure the conductivity. Okay. So you can record your reading anytime you feel that it is stable. It's sort of giving a relative normalized number there. Okay, so take your reading, and then we're going to rinse this, and then we'll put it in our next substance. Our next substance is sodium phosphate, seen here on the bottle. So we're going to put it into the beaker here now. And you can record your value now for sodium phosphate. Our next substance is calcium chloride. Put it in our beaker. And make your reading . Okay. Rinse again. Our fourth substance . I'm going to redo these. Okay, I've set this up now to give us both the numerical number as well as the graphical representation. So our first substance will be aluminum chloride, and I've put some in a beaker here. So I'm going to set it into the beaker. Okay, so anytime you felt you were ready in there, then we'll rinse it off. There was something else I had to push. All right, our next substance is sodium phosphate. Set it in our beaker. Okay. Our third substance is calcium chloride. our fourth substance, sodium chloride. Our fifth substance, now we're switching to our acids. This is hydrochloric acid. So you can use this number to tell me whether or not it's a strong or a weak acid. And our next acid is phosphoric acid. Our next acid is acetic acid. Right, that concludes the acid section. Now we're going to look at some other substances. So our first one we're going to look at here is what is actually the conductivity of our purified water. This is not, this is our particular purification method. This is not distilled water. Okay. Now we're going to look at some tap water from the faucet. And finally, we'll look at some ammonium hydroxide. This is ammonia in water. When you put ammonia in water, it makes ammonium hydroxide, or ammonia cleaner. And we'll put that in our last beaker here. All right. That concludes the data collection for this particular exercise. For your reference, the table and the graph are there. Your instructor may ask you to put them together in your own graph and submit it in a different format. That's why I've left you both the raw data here on the left-hand side, as well as giving you the graphical representation. They're also, generally speaking, clustered. The first four are our ionic substances, then our acids, and then our other substances, just like the parts in your lab today.
In part B of this laboratory, we're going to look at a few solutions and then look at them in combination. So what I've first done here is put our electrode into water, purified water, so we have a basis for our readings as our low. And then what we're going to do is going to take a solution A of calcium chloride and put it in beaker labeled A. And then we're going to put a little bit of A into beaker C. And then we're going to put this sodium phosphate into beaker B. And then again the same into beaker C, which will be our combination mixture. Okay. Just for consistent practices, we're going to rinse this and then take our first reading. By putting it into our first solution here. And keep. Okay, so that's our calcium chloride solution. And then our second solution here, which is our sodium phosphate. And if you look at our third beaker here, once we've combined them together, we have a precipitation reaction. We're going to look at the conductivity after they have precipitated.